Uh, Welcome back. I'm going to now look at another example where we have a pulley. So let's say I have a pulley here, and the pulley is tied to the ceiling, right? Tied to the ceiling so it doesn't fall. It's a massless pulley. And then you have two objects here. Let's say you have M2, and let's say M2 is 200 kilograms, and then you have M1, and let's say M1 is 100 kilograms. And as you might expect, the 200 will fall, and M1 will rise. M1 will rise. And the question is, what's the acceleration of each? If I didn't give you, if I kept them as M1 and M2, you would just assume you can just take the acceleration to be in a certain direction, and then go on like that. And then if you get the negative of what you thought it should be, then you would just put a minus. You know that your assumption was incorrect, and the acceleration is the other way. In this case, they will either fall down or rise up this way. Depends. If M2 is larger than M1, then they will go like this. If M1 is heavier, then they will go like that. If they're equal, then they will stay. If they had an initial velocity equal to 0, then they will just stay. So let's try to find what the acceleration should be. So it's a massless pulley. They're connected by the same string, and so that the first note is that the tension is the same because it's the same ideal rope. And the second thing is when this one rises, this one falls, and the magnitude of acceleration will be the same because this one rises by an inch, this one drops by an inch at the same rate, and they will have the same speed, and the speed change will also be at the same rate. So yes, this one will have an acceleration downward, this one will have an acceleration upward, but they're equal in magnitude. So I'm going to make this to be the positive y direction. I don't need the x direction because there is no motion this way. And we ask, here is object M1, what are the forces on M1? Well, there is the force of tension. Tension always pulls, and it's upward. I'll just call it the tension. And then there is the force of gravity on it, and it's M1 times gravity. And for M2, well, M2, there is the force of also tension, T, and then there is the force of gravity, M2G. What else could there be? There is nothing. It's not in contact with anything else besides a rope. So it's in contact with the rope, so there is tension. We have no normal forces here or friction or anything. We just have the earth pulling it down. And so we say, all right, the tension, let's look at M1 first, for M1. Yeah. The tension, it's upward. Let me write it this way. The net force on M1 will equal to M1 times the acceleration for M1. I could have called it A1, but let me just call it the acceleration for M1, just A. And I'm assuming M1 will accelerate upward because it's lighter. If my assumption, let's say my intuition was wrong, then I would get a negative number. What's the net force on M1? The net force on it is, you got a tension upward, and you got an M1G downward, and that should equal to the mass times acceleration, which is M1 times the acceleration. Okay, great. I don't know what the tension is. I know M1, but I don't know the acceleration. So I have two unknowns. Fortunately, I have another object here that I can find the net force on. So the net force on object 2 will equal to the mass of object 2 times the acceleration of object 2. Object 2, if object 1 rises, object 2 will fall, and so I will have a minus sign in here. That will be the relationship between them, meaning the acceleration of object 1 will equal to the negative of the acceleration of object 2. Okay? And so, here, this is Newton's second law, and then the minus sign here is and the acceleration has the same symbol, is because they are connected objects and they are restricted or constrained to move in a certain way, meaning they're tied by a rope. So one of them rises, the other one has to fall. That's the constraint. and the acceleration has to be the same. Okay, so I wrote Newton's second law plus the constraint thing. What are the forces on M2? You got the tension upward, and then M2G, it's downward. M2G, it's downward, and that has to equal to M2 times the acceleration. But remember, there is a minus sign because it's accelerating downward. Okay, what do I do with this? I have two unknowns. I can just subtract the two equations to get rid of the tension. Let's do that. Subtract the two equations. Here is equation 1. Here is equation 2. I'm going to do equation 1 minus equation 2. So this minus that. So you have t minus mg minus t. So the t cancels, and then minus m2g's. That becomes a plus. So we'll have m2g minus m1g basically. So I will have m2g minus m1g. I reversed the order. It's really minus m1g plus m2g because of the minus minus, but I wrote it this way. The tension cancelled. And then here, m1a minus m2a, that becomes m1a plus m2a, and we will factor the acceleration. So m1 plus m2 times the acceleration. And so I would factor g out. And so I have m2 minus m1 is equal to m1 plus m2 times a. And so the acceleration will equal to m2 minus m1 over, g times g over what? Over m1 plus m2. That's the acceleration. That's the acceleration. Let's see if this formula actually makes sense. If m1 is equal to m2, they're the same weight, the acceleration should be 0 because they should balance. And that's what this says. m2, if it's equal to m1, you get a 0, and then 0 times everything becomes 0. If m1 is heavier, if m1 is bigger than m2, then you would have a minus sign here, meaning the acceleration would be negative, so it would be in the direction opposite to what I expected, which makes sense. If m1 is more, if m1 is heavier, then instead of going up like that, this one goes up and this one goes down. If m1 is heavier, this happens. m1 falls and m2 rises. So that makes sense. And if one of the masses is 0, if let's say if this, or let's say if this mass is 0, if there is no m1, what happens to m2? It will just fall, and it will fall at the rate of gravity. So if m1 is 0, if you have a 0 here, you just have m2 on top, and then m1 is 0, you will have m2 on the bottom. m2 cancels m2, and the acceleration will be g. And so let's do it for the problem that we had in hand. The acceleration will be m2 is 200 kilograms, m1 is 100, and then I would have 200 plus 100, right? m2 minus m1, m1 plus m2. 200 plus 100, or 100 plus 200, either way, times 9.8. And so I would have what? 200 minus 100 is 100, and then 100 over 300 is 1/3. So it would be 1/3 of 9.8, and that's approximately what? 3.3, I think? 3.3 meters per second squared, approximately. I don't have my calculator handy at the moment. So what would the tension be? Well, you can calculate now the tension. The tension will be, I can use this equation. It would be, move the m1 to the other side. It would be m1g plus m1a. And so the tension will equal to, factor the m1 times g plus a. And so there will be m1 is 100. And then g is 9.8 plus 1/3 of g, which is approximately 3.3. And you will have the tension that way. All right. And then my last example will be two objects that are connected. Okay, they are connected. And let me do that right here. All right, so here is the next and maybe final example for this chapter. Here are two masses. Let's say I have M1. Here is a pulley. Again, it's an ideal pulley. And then here is mass M2. They're connected, and they will be accelerating. Let me make my thing focused here. All right, I got my camera to focus. So what happens is they're going to accelerate, and we're assuming now there is friction here. There is friction, UK, there is friction, because they're sliding. So they would be moving like this. This mass will move this way, and this mass will move this way. And the question is, what would their acceleration be in terms of their masses and mu k? So you're given M1, you're given M2, and you're given mu k. So what would their acceleration be? So for example, these are now numbers. Let's say this one is 2 kilograms, and this one is 0.5 kilograms, and this one is, let's say, 0.25. What would the acceleration be? So we want to work with symbols. So we look here, we ask, what are the forces? What are the forces? What are the forces on M1? On M1, you got, first of all, the force of gravity, M1G. It's resting on this surface, so it would be, not resting, it's interacting with the surface, so there would be a normal force, N. It's connected by a string, and the string would pull it, so there would be tension. And if it moves to the right, there would be friction, force of kinetic, would be kinetic friction because it's sliding. Are there any other forces? The answer is, I don't think so. I have accounted for all the forces. How about this object? This object is connected by the same string. The string is ideal, the pulley is ideal, and so there will be tension. And it's the same letter as T here. Whatever this one is, this will be the same. Yes, this one is up, this one is to the right, but the magnitudes are the same. And then there is the force of gravity, M2G. Anything else? I don't think so. And so they're moving, accelerating downward. And I'm going to set my axes. I will just give them both the same coordinate system. Here's the x direction, here's the y direction. And let's consider them just object by object. So let's look at M1. The sum of the forces on M1 in the y direction will equal to M1 times the acceleration of M1 in the y direction. Let's look at it. So the sum of the forces on M1 in the y direction will equal to M1 times the acceleration of M1 in the y direction. It's a mouthful. M1 is moving just along the horizontal. It's constrained to move along the surface, so it doesn't accelerate in the y direction. So the conclusion, this part here is 0. All right. So the left-hand side is 0. I'm sorry, the right-hand side is 0. What should I put in the on the left-hand side? On the left-hand side, what are the forces in the y direction? The tension is in the x direction. It doesn't have any y component. The friction is in the x direction. It doesn't have any y component. The normal force is in the positive y direction. And then M1G is downward. It's in the negative y direction, so it's minus. And so we conclude that the normal force is equal to M1G. Immediately, there is a force that's related to the normal force, which is the force of friction. So the force of friction, in this case kinetic friction, will be mu k times the normal force, which is M1G. Next, let's look at the net force on M1 in the x direction. In the x direction, again, the net force on M1 in the x direction. What are the forces? I will not rewrite this one. In the x direction, there is the tension to the right, and then there is the force of friction to the left. Anything else? No. And they have to equal to the mass times acceleration. m1 times the acceleration of m1 in the x direction. I'll call it the acceleration of m1 in the x direction. It's in the positive x direction, so I'll just call it acceleration of m1 in the x direction. So let me go here. So I get that the tension will equal to, or let me write it this way, the tension minus the force of kinetic friction, which is equal to mu k m1g, that should equal to m1 times the acceleration of m1 in the x direction. I'll come back to this acceleration of m1 in a moment. All right. So this is the equation I would like to save. Next will be, we're done with m1. We took the forces in the x direction, the y direction, the x direction, we're done. Let's look at m2. Notice here I have two unknowns, tension and the acceleration. Let's look at m2. M2 doesn't move along the x direction. There are no forces on the x direction for m2. They're only in the y direction. So the net force on m2 in the y direction will equal to m2 times the acceleration of m2 in the y direction. Okay, so the tension, that's upward, minus m2g will equal to m2 times the acceleration of m2 in the y direction. I'll write it this way, okay? And will it be accelerating upward or downward? Because we're up. If it were accelerating upward, we would put plus. It's accelerating downward, so I'll put a minus in here. All right, I put a minus in here. All right, so far so good. And I have this. I'll put in this. So now I have one unknown, a2y. That's another unknown. Two unknowns. This is the same unknown, so it's still two. But then a1x, a2y. That's. It seems like three different unknowns, and I only have two equations. And as you can tell, these are constrained to move together. So the conclusion that the magnitude a1x will equal to the magnitude of a2y, and let's just call them a. Let's just call them a. Because when this one falls, this one moves to the right. They're connected. Okay. So we rewrite that one. The first equation would be t minus mu k m1 g is equal to m1 times a, times the acceleration. And everything is positive because it's to the right. And then for this one, I'll put t minus m2 g is equal to minus m2, and instead of a2y, it's just a. Everything looks good. And I don't want the tension, I want the acceleration, so I will just subtract these two equations. I'll put this minus that. So let's see what we get when you subtract them. T minus t is 0, and then minus mu k m1g minus m2g. This becomes a plus when you do minus minus. So you would have m2g and then minus mu k m1g is equal to m1a minus m2a, that becomes plus, so it would be m1a plus m2a, so that's m1 plus m2, we factor the a out. Factor the a out. So, now I will calculate the acceleration. So I will get the fact that the acceleration will be, I would factor g first, so it looks better. So I have m2 minus mu k m1 times g, is equal to m1 plus m2 times the acceleration. And so we conclude that the acceleration would be m2 minus mu k m1 minus g over m1 plus m2 plus m2. Okay. And that would be it. That would be it. So for example, let's say M2 is equal to 1 kilogram, mu K equals to 0.2, and then M1 is, let's say, 2 kilograms, or let's say it's 1 kilogram also. M2 is 1 kilogram. So the acceleration will be M2, that's 1, minus mu K times M1, that's 0.2. 0.2 times 1 is 0.2. 0.2 times 1 over, and then G here, 9.8. I'll just keep it as G. And then 1 plus 1 is 2. 1 plus 1. And 1 minus 0.2 is 0.8. 0.8 over 2 is 0.4, so it will be 0.4 times G. Fine. Here's a question for you. What if M1 is so large that M2 minus mu K M1 will be a negative number? What would that mean? What would that mean? That would mean, if the acceleration is negative to what we thought, it means it's in the reverse direction. Would you buy that? If I make this so heavy, then suddenly this mass will start to rise and this mass will start to move to the left, just spontaneously like that. What's wrong? Or obviously that's wrong, right? It cannot just, you have two masses, you let them go, and then they just start, this one rises and this one moves to the left. That'll be wrong. What's wrong? The answer is, when you derive a formula, remember the assumptions under which you have derived it. We have derived this equation here, this one here, under the assumption that the friction is to the left, meaning this block is moving to the right and this block is falling. If you see, friction does not make up its mind. It's to the left if you move to the right, and it will be if you move to the right, to the left, friction will be to the right. So then this formula will not apply in that case. So imagine like somebody comes and then just shoves this one to the right, gives it an initial velocity this way, and this one starts to rise. And the question is, what would the acceleration then be? Then you have to go back to this free body diagram. You will have the tension to the right still, but friction will be to the right also, and then you analyze the problem that way. Eventually, they will move, and then they will come to a stop, and then maybe come down again later. So the point of this is, remember the assumptions under which you have derived a formula. So, right, just like in math, right, when you have a theorem, they will always say, assuming that this and this and this, then this theorem applies, right? For example, if you have something I can recall probably, I hope it's accurate. For example, in the mean value theorem, it says if you have a function that is that's continuous on an interval, including both ends, including the endpoints, then you can have the derivative of that function equal to the slope of the line secant that goes through the 2 points. Assuming those assumptions hold. Now, they always trick you. They'll give you a function that's not continuous at the endpoints. It doesn't include the endpoints. And then the theorem fails. And so always remember under which assumptions you have derived that formula. And it only applies to those assumptions. If you wanted to apply more broadly, then you have to derive a different formula that's for that broader or different situation. All right, I will see you next time when we do chapter 8, Newton's dynamics in 2 dimensions.